But we can also think when we're talking about the wave function squared, what we're really talking about is the probability density, right? The probability in some volume. But there's also a way to get rid of the volume part and actually talk about the probability of finding an electron at some certain area within the atom. And this is what we do using probability density or radial probability distribution graphs. And what that is the probability of finding an electron in some shell where we define the thickness as dr, some distance r from the nucleus. So think about what we're saying here. We're saying the probability of finding an electron at some distance from the nucleus in some very thin shell that we describe by dr. So if you think of a shell, you can actually just think of an egg shell. That's probably the easiest way to think of it, where the yolk, if you really maybe make it a lot smaller, might be the nucleus. And let's also make our egg perfectly symmetric and perfectly round. But still, when we're talking about the radial probability distribution, what we actually want to think about is what's the probability of finding the electron in that shell. Think of it as that egg shell part. So we can do that by using this equation, which is for s orbitals, where the radial probability distribution is going to be equal to 4 pi r squared times the wave function squared dr. That should make sense to us because when we talk about a wave function, we're talking about a probability divided by a volume because we're talking about a probability density. So if we actually go ahead and multiply it by the volume of our shell, then we end up just with probability, which is kind of a nicer term to be thinking about here. So, of course, if we're talking about a perfectly spherical shell at some distance, thickness dr, we talk about it as 4 pi r squared dr. So we just multiplied that by the probability density. We can graph out what this is, where we're graphing the radial probability density as a function of the radius. And what you see is that at 0, you start at 0. And so the radial probability density at the nucleus is going to be 0, even though we know the probability density at the nucleus is very high. That's actually where it is the highest. The reason in our radial probability distributions we start, maybe this one will do it. No. OK. The reason, if you look at the 0 point on the radius, that we start at 0 is because we're multiplying the probability density by some volume, and when we're not anywhere from the nucleus, that volume is defined as 0. So it's a little bit artificial that we're seeing that 0 point there. So actually, I want you to go ahead in your notes and circle that 0 point and write not a node. This is not a node because a node is where we actually have no probability density. So this, where we start at 0, is not a node, is the first thing to point out. And as we get further and further from the radius, the volume we're multiplying it by actually gets bigger and bigger because you can see how the volume of that little thin shell is going to get larger and larger as you get further away. So there's some distance where the probability of actually finding an electron there is going to be your maximum probability. And that's what we label as r sub mp, or your most probable radius. This is the point at which your probability is highest for finding an electron. This is equal to a sub naught for a hydrogen atom. And we remember that that's just our Bohr radius, which is 0.529 angstroms. And basically what that means is you can actually find an electron anywhere going away from the nucleus, but you're most likely to find it. You have the highest probability at a distance of a naught, or the Bohr radius.